Can anybody confirm whether they're able to log into that lab and see their work and see the lab?
Yeah, I can see it.
Okay. All right, so let's begin. Looks like my screen here is a little too zoomed in. Although since you're all on your own screens, I guess it doesn't really matter what this one looks like, but. Okay, let's start with a quick little warm-up activity. Okay. So what I'd like you to do is let's just watch again, just to remind ourselves. I'm sure many of you did it recently, but who knows, some of you might have done it 4 nights ago, 3 nights ago. But this was what the general idea of what we were watching. On other trials, we've seen. Where was the other video? I thought there was 2 videos. Oh, do I have to load it? Load them separately? Yeah. Trial 2. Something more like this. In this case, it makes it a lot more obvious that the card on the left is probably a lot heavier than the card on the right. I mean, they all look like they're, you know, high school kids. Those two people on the left surely collectively weigh more than the guy on the right. It's got to be true. Maybe not as obvious in the first one. But let's go ahead and watch this again. Okay, so what I'd like you to do is to jot down a few ideas on your own. Maybe 5. I'll ask you to see if you can come up with 5 ideas that you learned, what you consider important notes. That if somebody had come to you, maybe you have a cousin that's taking AP Physics, let's say, for example, and they say, "Oh yeah, you did that. What did you? I skipped it, or I didn't do it." What were the main ideas of it? Can you tell me? What would you share with that cousin? I again challenge students to jot down 5 what you consider important ideas learned from this particular lab. And then we'll, in a few minutes, we'll have you guys share what you learned. You want to jot it down on paper? That might be a good idea. Of course, it takes a fine eye to learn anything, but you guys have developed a pretty keen sense of seeing and measuring using this pretty precise tool that we have here. You know, at first glance, the average person would say, "Well, I didn't learn anything. 2 people pushed off each other." That's it. But with, again, a keen eye and careful observation and ability to make precise measurements, there should have been a number of things that you guys actually considered important ideas, in my opinion. If you can't come up with 5, don't feel bad, but just try to come up with, maybe I shouldn't put a number on it, but just as many as you can think of. What are the big ideas? And I don't consider like you saying, the guy had, whatever, 5.27 units of momentum. That's not a big idea. That's a data point. Nobody cares about data points. I certainly don't. I care about ideas that might be something that came from looking at the data points, right? Like a trend. Well, that's an idea. Like it was this value, then it was this, and I could see that this was trending in this way, this one was trending in that way, and you're analyzing data and coming up with some idea, then yeah, I'm on all board with that. I'm just referencing, or letting you know, referencing some particular number and say, I learned that, something specific. His speed was 2 point. That's not a big idea. So think of it as in concept, an idea that should technically be able to apply to any variation of this experiment. And if it's a big idea, then that idea should be observable in all variations of the same experiment. So I'm going to give you just a couple minutes. After that, I'm going to actually give you some points to think about. I, as the teacher, know a fairly large list of things that I would want students to learn about just from this one lab. But I want it just to be an open inquiry question, which it is right now. Just jot down what you think you learned. In a minute or two, I'm going to give you like a list of things that I want you to think about. Like, all right, now here's my list of big ideas. What did you learn about idea number 1, or what did you learn about idea number 2? And then we'll talk about them. And again, if you're in your mind like, not sure, well, think of all the topics that are in this unit. What are the topics we teach? Momentum is a topic, obviously. Conservation of momentum is a huge idea. The vector nature of this conservation law is pretty important. And that actually ends up playing out here because you have one moving to the right, one moving to the left. And that distinction in direction becomes important when you're talking about something's value as a vector. Remembering leftward pointing vectors would be considered a negative contribution. Rightward pointing vectors would be a positive contribution. Then after we talked about conservation laws, it was, well, what are the details of the conservation law? What actually happens between the two people while they're pushing on each other? We call that the mechanism. The mechanism for the momentum changing. Mechanism in science is just a physical description as to what's actually happening that causes that. Like, what's the mechanisms for cancer? Well, we can say, smoking or doing this or doing that causes cancer, but that's not a mechanism. That's just an act. Smoking is the act. If you're wondering what the mechanism is, you'd have to be on the cellular level and think, all right, there's lung tissue and there's cells, and some sort of mutation happens on a cellular level, eventually turns into tumor. And now you're really describing the physical process. That's called a mechanism again in science. So we know, again, we see that their momentum changes. What are the mechanisms? What causes that? So the mechanisms are impulse. Mechanism is the impulse. I mean, that's not necessarily specific. That's like the mechanism, one mechanism for cancer is smoking. Smoking isn't very specific. I mean, it's an act. It tells us that doing that might cause such and such, but I wouldn't cause it the mechanism. The mechanism, again, is a very specific details inside your body, what's actually happening that causes that. So what causes the change in momentum? Impulse. It's a good starting point. What is the mechanism for impulse? What's the details there? Well, they have to push on each other. You might think, is that even necessary? It's another interesting idea just to think about. You can see that, it looks like they are actively pushing off of each other in the sense that, she's pushing to the right on his hands. He's pushing to the left on her hands. And looks like they're both kind of putting some energy into this, right? After they coast off, they have some kinetic energy as they coast away. Where did the kinetic energy come from? It comes from the work that they're doing during this time, the force times the distance, right? And so where does the energy of kinetic energy come from as they coast away? Does that kinetic energy just come from the work that she did? Does it come just from the work that he did? Or does both their kinetic energies, or might we call it the system's kinetic energy, does it come from the work done by both of them? Technically both, right? They're both putting some energy into this interaction. And that work, force times distance that she does, plus the work that he does, force times distance that he does, added together should turn into some kinetic energy for the system. And that manifests itself as them moving away with kinetic energy as a system. That would be the sum of their kinetic energies. The sum of those kinetic energies should be equal to the sum of the work done here. And here I am talking about work and energy, and that's not even the right unit. But technically, we are in the energy momentum unit. Additionally, I was saying the mechanism for their momentum changing, again, is the force that they're applying and how long in seconds they're pushing on each other. What I was trying to point out is, what if he wasn't actively pushing on her, but he was just kind of like holding up, I don't know, a book, holding up a textbook sideways, just like out with his two hands. And he wasn't necessarily trying to push her hands towards her. He was just kind of steadily holding the book there. And I would call that a non-active participant. He was just kind of like a wall. Yet she was the active pusher. She was actively trying to push off of him. Do you think that that would have produced different results than him actively pushing against her while she actively pushed against him? Again, he truly is probably trying to push her hands to the left. It's like they're fighting against each other. Again, my point is, what if he wasn't and he was just holding a book in one spot and letting her push her hands against his textbook? Any ideas there? Would that have changed the outcome in terms of the speeds, do you think, that they have as they coast away? Anybody? Yeah. A little louder? Would it, when you say it slow down, what's it? Oh, I see. Would they come away from that with less speed? Would the effect be that they move away slower with less speed? It's certainly a good guess. What makes you guess that? What would your justification for that be? So just stop there, just because I sometimes, if someone goes too far, I want to repeat what you're saying so people at home can hear it. Miles is saying that he thinks a justification for my question, and he answered it, that he thinks if he was just holding the book up and letting her push it, that they would ultimately coast away with less speed in that experiment than we currently see. And the reason is because he's not doing any, he's not applying any force. He's just holding the book. She's the one that's applying the force. So now keep going. Reasonable. It's just a sound justification. He said and then he turned his attention to work in his description and said, well, the total work would probably be less, because if he's not using any force and she's the only one that's doing force times distance, then she's doing work and putting some energy into the system, but he's just like a wall. Then he's not doing any work. And therefore no energy is really being contributed to the system from him. Any other thoughts? It's a very good description. I'm not saying it's right, I'm not saying it's wrong, but any other thoughts on that anybody has? No other thoughts on that, huh? Is it true? Oh, go ahead. Little louder if you don't mind. You start out loud and I hear you, but then it gets really quiet and I really have a hard time understanding at the end. Just what's the last part? So they move in the same direction? Yeah, maybe, certainly possible. Certainly a good thought. What would your rationale and justification for that be? Mm-hmm. Mm-hmm. Okay. Seems good. Seems good. Any other thoughts about this? This is an interesting question. This is the kind of question that they'd probably put on a free response question, like a hard one. Like, boy, I really kind of have to think about that. They do that. They'll do that to you. Scenario here, and they say now write about what the change would be if the person was just holding the book. Oh, go ahead. Yeah. Oh, so I'm just going to comment that Roland is mentioning Newton's third law. Why is that important? When the push from the large cart onto the textbook. Math. Yep. So Roland continued to say that as they're pushing, the idea of Newton's third law is that those forces will be in opposite directions, right? Who will feel the greater force during the push? The heavier one, the lighter one, or neither? The heavier cart, the lighter cart, or neither? Who feels the greatest force during that push? The stronger pusher, the weaker pusher, neither? The heavier cart, the lighter cart, neither? I don't know. Any combination of those? Yeah. The heavier cart? Because? Where's your because statement? Makes sense, right? The heavier cart would probably push harder than the lighter cart because it's heavier and it resists being moved, so it kind of pushes back harder, right? Is that what you're thinking? I think I've actually thought that as well at times in my life. Any other thinking here? What do you think, Matt?
They're all the same.
Or Julian? Was that Julian? Go for it.
Yeah, they're all the same.
Why do you think they're all?
They're both applying the same force.
Why do you say that though? I mean, isn't maybe he stronger than her, or it could be her stronger than him. I mean, you could. Let's just replace it with me.
They move at different speeds when they are in motion.
That's in fact what Roland said, which I didn't share with you. He said, though they feel the same force, he said their acceleration should be different because Newton's second law, right? He said acceleration is inversely proportional to mass. So, though Roland's claim was though they must feel the same forces, the heavier one will move less distance during the push, and the lighter one will move further distance during the push. And you're continuing with that, Julian. Go ahead. You were saying something similar, that the forces would be equal, right?
Yeah, and that because of that, their impulse would be the same, and also the force that was applied on them is the same. They're equal and opposite.
Yep, nicely said. Now Julian's finishing, actually taking off from where you left off, saying, because of everything you said, and the forces being equal, and since when I say forces being equal, I mean the force that one person feels as they did this experiment compared to the force that the other person feels as they did the experiment. Since those would be equal amounts of force, that's actually Newton's third law. Heavier one, lighter one, stronger one, weaker one, that actually ends up not mattering. Newton's third law says forces always come in pairs. If one thing feels a force, the other thing that it's interacting will feel the exact same amount of force, but opposite in direction. It's unavoidable, no matter how big one is or little one is, how strong one is or one weak one is. He said it doesn't matter. All forces come in pairs. They're always equal amounts of force and magnitude, but opposite direction. And now Julian's saying if that's true, and they're pushing on each other's fingers for the same amount of seconds, then the impulse that they both experience should be the same, since impulse is force multiplied by how many seconds they're pushing on each other for. The force is the same, time is the same, the product must be the same for both. Their impulses should be the same, you said, Julian, right? And therefore, who should have more momentum coming out of this push?
They have the same.
The heavier one, the lighter one, which one should have the more momentum in the coasting away phase of this? Which, the heavier one has more momentum or the lighter one has more momentum? Yeah. Right? That's a reasonable guess. The lighter one, somebody would definitely, and this would be like a Susie says, Jimmy says, describe what's right, which might be wrong. And that's kind of what we're doing now. And I don't mind that because it's good practice. This lighter guy, based on what Roland said, the lighter guy should have a greater acceleration during the push. His speed should be increasing at a little faster of a rate than these people because he's got less mass. And if he has less mass, then he has a reduced acceleration. This person on the, I'm saying, because he has a less mass, he has a greater acceleration, what I meant to say. This person, on the other hand, is heavier, and the extra weight or extra mass means they'll be accelerating at a slower rate during the push. This person is then, you guys should have been able to collect evidence for the fact that this guy's speed on the right is faster than their speed on the left. I haven't done the lab, but it has to be true because everything we've said is true so far, and those are laws of physics. So most people would actually say what you said, Miles. Miles said, I believe that this guy on the right would probably have more momentum because he's moving faster. That's right in line with what a lot of people would say. But then they'd say, but then Billy says back to Miles, yeah, he's moving faster. And that you're thinking that probably gives him more momentum because momentum involves how fast you're moving, speed. But this person says back to Miles, yeah, but momentum also involves how much mass you have. So though he has lots of extra speed compared to the girls, he has less mass than them, and momentum is actually mass times speed. What do you say back to me then? Exactly. If they did provide the same force to each other, because it's unavoidable, it's Newton's third law. If the time and period that they're pushing on each other, again, that's, I don't know, some amount of seconds during the push, I don't know what it is the same, then the product of those, called impulse, must be the same for both. And then impulse is equal to how much their momentum changes. So when you multiplied force times time, if it came out as 5 units, we'd say that the girl cart received 5 units of impulse. The guy cart received also 5 units of impulse because force is the same for both, time is the same for both. Someone said, what is the change in momentum for the girls? It's equal to whatever impulse they received. 5? Oh, they've got 5 units of momentum, therefore, coasting away. How much momentum does the guy have? How much impulse did he receive? Also 5. So he's got 5 units of momentum coasting away. But Billy says back, how can that be? Because he clearly has more speed. How could they have the same momentum? Because, anybody? How about at home? How is it that this guy on the right can have the same momentum as the girls on the left if he's got more speed? Matthew Arndt. And I'm pronouncing your last name incorrectly, I'm sorry. Oh, I can't hear you. Try again. I saw you unmuted yourself, but then as you spoke, there was no sound coming through. Or is it on my end? Can you speak, Matt? Oh, nothing. All right, sorry. You might have let me see if it's my issue or your issue. Catherine, can you say something?
Hi, do you want me to answer the question?
Yeah, you go for it. I'm sorry, Matt, but you must have a mic issue right now. Go ahead, Catherine.
Well, like you said before, because momentum is mass times velocity, since the guy has more velocity on the right, but the girls have more mass, so it'll end up balancing out.
That's right. Yep. So let's just use the numbers 2 and 5 for mass and velocity. Let's just say that his mass is 2 kilograms and his velocity is 5 meters per second. Let's just say in my example, if he was 2 kilograms with a speed of 5 meters per second, his momentum would be 2 times 5, which is 10 units. If that were true, how much mass would they have? if his mass was 2 and his speed was 5 coming away, their product on the left also has to come out as 10. So that means they would be 5, they would be the switch. He says, my number 2 references my mass. My number 5 references my speed. They'd say, oh, that's interesting because my 5 references my mass. Your 5 references your speed. He'd say, yep. And they'd say, well, that's my mass. And they say, that's also interesting because what was your speed? My speed was 5. This guy over here, his speed is 5 and his mass is 2. So it's the reverse for them. Their mass would be 5 and their speed would be 2. What would the product come out for them? 5 times 2, 10. 5 times 2, 10. How about for him? 2 times 5, 10. That's the idea. That's a big idea. It's a huge idea. I'll lastly say, because I never answered it, even if he's not actively pushing, even if he's holding a book there, if she pushes with 5 newtons of force against his hands, against the book automatically pushes back with 5 newtons of force. It doesn't have to be alive to push back. You could build a wall here. You could build a concrete wall on the edge of the cart and have it be the weight of the guy and mount it onto the cart and let her push it. She pushes with 5 newtons on the right of this wall. The wall pushes to the left on her with 5 newtons of force. You remove wall and you put a live object called the human being. You say, all right, girl, push again. She's like, all right, here I go. And she pushes with 5 newtons of force against his hands. He pushes back with 5 newtons of force against her hands, even if he was just holding his hands there and she was just pushing against his hands without him doing anything actively. In the next scenario, she's like, now you push against me while I push against you. Here I go. And she pushes with 5 newtons of force against him. Guess how hard he's pushing against her? While he tries to push harder than her. She could only push with 5 newtons of force to the right. And he's like, but I'm going to really push into you this time. How hard is he pushing back on her with? How much force if she's pushing on him with 5? That seems reasonable, right? Most people would say what you said. Hey, if he's actively pushing harder in this next trial, and she's pushing with 5 newtons of force into him, but in this next trial, he's like, I'm going to really push against you hard while you do that 5 newtons of force. Roland said, well, he must be pushing back on her with 5 newtons plus some extra because he's trying really hard that time. But what does Isaac Newton's third law say about that? Precisely. So there's the idea is that you can't avoid the fact that at all times the force that one feels to the right is exactly the same as the force that one feels to the left. That's Newton's third law. It makes sense what you said, that he must be pushing a little harder if he's putting effort into that one more than her, that he's pushing with more force than she is. But they always feel the exact same force at all times. It would be true, however, if he was actively pushing and she was actively pushing. Is he exhausting some energy? Like, is he a little tired from doing that after? Oh, I'm tired. Yeah, I felt that. I put some energy into it. She'd say, oh, I felt that too. I put some energy into it. How many people are putting energy into it? 2 people. What if he was just holding up his book? Would he be putting as much energy into that by just holding the book still while she pushed? No, right? So he in fact wouldn't be putting really any, because if his distance is, his arms aren't moving, the distance the book moves would really just be, it's just still the whole time. So there'd be less energy put into the system if she's the only pusher. There'd be more energy put into the system if they're both pushing. So technically they'd have greater speed coming away from each other when they both push versus if just one push. All right. Those are, yes, it's an interesting idea. It's an interesting lab to me, and maybe to some of you. I'm going to at least show you now how to model that, and then we're going to go on to other things. In fact, I think I'm going to give you another lab today because this is just a really good topic for doing labs. They have a lot of really good labs on Pivot for this topic. So let me just pull out my camera as I do that. So to summarize, Momentum of the guy going to the right and the momentum of the cart going to the left will always be equal no matter what. You could take two descriptions for that. You could say, well, again, the pushing force is they feel is always the same, Newton's third law. The time they're pushing on each other is always the same. The product for both people, force and time, is going to be the same number. We call that impulse. And that number is their change in momentum. So they both have the same change in momentum. If they both start with zero momentum, they both must be moving away with the same momentum. You could take that approach. Let me, hold on a second, get this activated. The other approach you can, and that's using like the details of impulse to describe why they would have the same momentum going away from each other. Instead, another student could say, it's just a conservation of momentum. What is the total momentum of the system before they push? The total momentum of the system has to be the same as the total momentum of the system after they push. You say, okay, before the push, there's no momentum. So after they push, after they've just separated, what would the total momentum have to be? Conservation of momentum says it's got to be zero, because that's the conservation of momentum law. That whatever the total momentum is before the push, it has to be the same as the total momentum after the push. If the total momentum before is zero for the system, then the total momentum for the system after has to be zero. How can that be? Well, if he's moving to the right with 5 units of momentum and she's moving to the left with 5 units of momentum, her leftward momentum is -5, his rightward momentum is +5, that adds up to 0. That's another way of defending the idea that they must have the same momentum. You can either take the conservation description and argument, or the whole force and time and do the whole impulse momentum idea. But no matter what, you can't avoid it. They'll both always have the same momentum. The heavier one will always be moving slower, as Roland said. The lighter one will always be moving faster. The heavier one will have a slower acceleration during the push. The lighter one will have a larger acceleration during the push. Ooh, let me actually see if you guys can answer one last question. Which cart would have the most kinetic energy? I guess that should be the final dagger question, because that's a doozy. Let out your fast roll and let everybody process that. This is my final question. We claim that they both have the same momentum. They don't have the same mass. They don't have the same speed, but their momentum's the same. Now, the final dagger question would be, does the guy have more kinetic energy than her? Does she have more kinetic energy than him? Or do they have the same kinetic energy? One more second. I got two people that want to share, but I'd like everybody at home to consider thinking about that again. It's a tough question. In fact, I would like to hear what you guys have to say, but I've heard from both of you, I think, multiple times. I'd like to hear from William. Are you there, William?
Yeah, I'm here.
Did you hear my question?
Yeah.
What do you think? Who would have more kinetic energy in this scenario? The guy cart coasting to the right after the push, or the girl cart system coasting to the left after the push?
The guy going to the right.
All right, guy going to the right. That's a statement or a claim. What's your justification for it?
I just use like the formula for kinetic energy, which is like 1/2 mv squared, and since I don't know, I was in between if it would be the same or the guy on the right, because he has more speed and the speed is squared. So
Ooh, I like that.
I was trying to think it through.
So so William said, I think it's the guy on the right that it probably would have more kinetic energy, and he's admitting that there is this difference between mass and speed, and that kinetic energy involves mass and speed. And he's like, yeah, he has less mass. He does have more speed, but the speed is squared. So if he's got the more speed and that's a number that's squared, then that probably will overcompensate for his little bits of less mass. That's solid. That's a solid description. I'm not saying it's right. I'm not saying it's wrong. Does anybody else? I want to hear from Roland, because he was not. You were going to say the square. I like the square. What were you going to say? You had your hand. Square as well. What were you going to say? Interesting. You were all thinking about the square. Wow. Anybody at home take a different approach on that? Matt S., what do you think?
So I was like in between on whether it would be the same or whether it would be the guy on the right, because if you think about it from like a work perspective, they both start with zero kinetic energy, but when they move, the person on the right, like when they're pushing on each other, he like moves a greater distance.
Can you hold on 1 second? I'm so sorry. I should be able to have this where I shouldn't have to repeat, and I've done that before, and I'm sorry that I don't have it that way. I'm gonna just change my settings. All right. Can you speak now? We should all hear you. Can you try again?
Yeah, so I was in
we go.
between about whether it would be the same kinetic energy or the person on the right has more, because if you think about it from like a work perspective, they both start with zero kinetic energy, but the person on the right, when they're applying force, moves a greater distance than the people on the left. So if it was force times distance, I guess it would be a greater amount of work. But thinking back to like the momentum thing about how one has a greater mass, but one has a greater velocity, so it like cancels out with each other. I would think that would be the same with kinetic energy, but since the velocity is squared, that makes sense that the person on the right would have more.
Nice. Nicely said. Everything you all said was correct. Those are just two different viewpoints of the same thing. The guy on the right would have more kinetic energy. You could describe it in two different ways. You could say, yeah, he has more speed, and yeah, he has less mass, but one of those things that he has more of is actually squared, which even further enhances the contribution to kinetic energy because it's squared. The other one is maybe not as obvious. It would take maybe somebody pointing that out, which I'm going to just lastly do, if you don't mind. If I took my ruler, it's not giving me a ruler. Oh, it's a tiny little ruler. Okay. So all I wanted to do was just point out that let's just see how far she moves. I'll put it right where her hands is here. So how far does she move? Actually, that was a bad choice. Take that back. So sorry. Because their hands will be in the same spot. And that's interesting, actually, to think about that, right? The hands shouldn't really move. Like the spot where they're pressing each other almost stays in the exact same spot, because what is the net force in that spot? In between is zero. Yeah, there's no net force in the middle area, so you can think of that as a point that should kind of stay in the middle. So my choice was poor in terms of where I put my ruler. I should put my ruler, like, I don't know, in this back of this girl's, back of her shoulder or something like that. To just measure how far does she move during this. Oh, shoot. Sorry. How far does this leftward one move during the push? And stop. Looks like her leftward shoulder went 26 or so. 26. Yeah, about 26 centimeters. Now, if we did the same thing for the other guy, will he also move 26 centimeters? Go back to the beginning. I'll put this, I guess, right on his back right here. All right. He's gone over 50 centimeters. I know, sorry, I didn't zoom in for you guys in class, but his back moved a full 50 centimeters. So that's evidence that his cart moved a lot further than their cart. Why? What Roland said in the beginning. He's lighter and his acceleration is higher. And if it's the same amount of seconds, he moved a greater distance. How do we calculate that distance? 1/2 AT squared. A would be whatever his acceleration was. T is how many seconds he was moving for. The bottom line is what Matt was saying was also correct. Work, he said, is force times distance. The force is the same for both, but he moves the greater distance. So the amount of work done on him is the force he feels times a great distance. The amount of work done on her is the same force times a small distance. So there's more work done on him, less work done on her. Matt mentioned the work kinetic energy theorem and said, well, if more work was done on him, then his change in kinetic energy has to be greater. If less work was done on her, then there must be less change in kinetic energy for her, and therefore he must be moving with the greatest speed to the right. That was nicely done, Matt, as well as everybody else. Those are all great answers. And I'm just pointing out, like, these are doozy of a question. Like, this is what they will do to you on their free risk, but they'll pick some of these really juicy ones where, like, there's so many different things to think about that it can get kind of confusing when you're like, mass, speed, which one is, you know, the more important thing to think about. When you get confused with mass and speed and you're not sure which way to go, just go back to one of the laws, like the Impulse-Momentum Theory or the theorem or the work kinetic energy theorem. And if you just keep it in one of the laws you're thinking, you can answer the questions generally without getting too caught up with, well, this one's got more mass, this one has less speed. And then when you do, again, go down that route, you start pulling your hair out. All right, I'm going to now just quickly show you one thing and then let you guys use the remaining time to start a lab. I tried before and then, oh, it's still here. All I wanted to show you was that the way that this is typically written for this type of problem, called the explosion or, you know, people pushing off each other. Just remember that the total vector momentum initially has to be equal to the total vector momentum after. When I say sigma, I mean, you know, for the whole system. Oh, so sorry. I will change that right now. Yep, thank you. So when I write sigma, it means like the whole system. Add up the momentum of the whole system. Initially as a vector, and after something happens, in this case after the push, have to be the same vector momentum. So I'm just pointing out for this explosion type of question, I don't know what else to call it, but that's, I know what I've read in textbooks, they call it explosion again. Remember that there's zero momentum before they go flying off in different directions. And again, that tells us that whatever we get from these two pieces, this might be the momentum of cart A, vector-wise, plus the momentum of cart B, vector-wise, that those two momentums as vectors have to add up to zero. The only way two vectors can add up to zero, if cart A was, let's say, the girls that were going to the left, and cart B was the guy that was going to the right, the only way you can get two vectors to add up to zero is if they're the same magnitude, same quantity, and in opposite directions, right? So if this was -5, this one was 5, right? That means they must have the same momentum in both directions. What I'm pointing out is, if you were to move one term to the other side, you'd end up with negative momentum of cart A, because I can move it over to the left, just like regular algebra, bring it to the side as a negative, equals this piece, the momentum of cart B, as a vector. And then I can now just re-express momentum by taking out of that neat little package called P and saying, well, it's technically the mass of cart A times the velocity of cart A, where this is technically speed, because I've already accounted for one's going to be negative and one's going to be positive. And that has to be equal to, and then I would re-express cart B as mass of cart B times the speed of cart B. And these are F's for, you know, their final speed after they push off. Why is there a negative parentheses and then no negative? Because of before, -5, right? One was going to be like a -5. That's like negative, this is like 5. And this one would be like 5, right? And so my point is, when you're solving for a final velocity, I'm just last point to you, usually on an AP exam, they're going to do what the lab did, which is based on the information we're giving you, find the speed or velocity of the other cart. You would just be solving it for V of cart B. If that was the guy's speed or velocity heading to the right, you would just solve for that algebraically. In fact, I take that back. My apology. That isn't speed. That would still be velocity. My apologies. So you'd have a negative mass of, you know, cart A times the velocity of cart A. As I should put a vector. I don't know why I thought it was speed. It's incorrect. So I'm just putting the vector back over that, saying that is a velocity vector. And then I would have been dividing by mass of cart B because I'm solving for the, usually this is the unknown. You divide by at mass of cart B. So let me lastly point out that the masses can be thought of as a ratio, mass of cart A divided by mass of cart B. That's an important thing to recognize. So that means the velocity of this guy, he's cart B coasting to the right, of cart B, F, velocity of cart B final is equal to the ratio of the mass of cart A divided by the mass of cart B. That ratio came from the fact that I had to divide over my mass of cart B over to this side, and then it puts a mass of cart A divided by mass of cart B. And I can now look at that as one thing because they're both masses as a ratio multiplied by the velocity of cart A. This is a super useful thing to know. Actually, it's supposed to be a negative here. Sorry, it was my negative. I just forgot the negative. Why I'm saying that is if the girl card is on the left, A is on the left, B is on the right, if their card is twice as massive as the guy, then what will his speed be compared to their speed? Again, just in your mind, girls going to the left is A, guys going to the right is B. If the cart A with the girls was twice as massive, let's just say they were 100 kilograms total, and well, that's a little too late. Let's just say there were 200 kilograms total, and he was 100 kilograms total. They were twice as massive as him. How would their speeds compare? If I had done that and I put in 200 kilograms for the girls' mass, for mass of cart A, divided by 100 kilograms if that was the guy's mass. What is 200 divided by 100? It's a factor of 2. That means whatever the girl's velocity is coasting to the left, let's just say they were coasting to the left, the girls, this is the girls. Girls are coasting to the left with 5 meters per second of speed. Well, will his, in fact, that would be -5 if they're going to the left, because of the vector. Then what would his velocity be? 2 times 5, which is 10, right? Why would he have twice as much speed? Because he has half the mass. What if they were 3 times more massive than him? Then he'd have 3 times as much speed as them. Or if they were the girls were 4 times as heavy as him, then the guy would end up having 4 times as much speed. Or you can word it this way. If the girls have twice as much mass, they'll have half the speed of him. If the girls have collectively 3 times as much mass as him, they'll have only 1/3 of his speed. If the girls are 4 times as massive as him collectively, then they'll only have a speed that's 1/4 of his. And that's what this gives. Those ratios come out from this mass of cart A over mass of cart B. All right, because that's all I wanted to show you. I just know that, if you get this as a free response question, part A might be derive a formula for, the velocity of cart B in terms of mass of cart A, mass of cart B, and the velocity. If they ask that, and sometimes they do on a free response, this is how you would show that. It all starts with showing that the total momentum starting with a 0, so whatever their momentums are after as a vectors have to add up to 0. All right, I'm gonna activate another lab. I'm trying to catch up to the labs as best I can. I've obviously asked you to do a lot of them, and I'll tell you, it takes a while, to grade them. Well, the ones that ask a lot of questions, that takes a long time for me to read those through and grade them. I'm doing the best I can. Let me jump back. I am going to give you this new one that's called copy of ballistic physical pendulum. So let's just assign it to you. And we'll take a look at it together. And then you can begin working on it. This is definitely a favorite for AP. That's why I'm picking it when it comes to free response questions. This does turn up sometimes as a free response question, and I'll tell you why in a minute. Word ballistic means something is being shot, like a projectile. A ballistic is like a projectile. And then pendulum, well, you know what a pendulum is. That thing on the right is a pendulum. It's a wooden pendulum. So this is totally the lab to end with. This is probably one of the last labs I do with you for this unit. Because this unit, I'm sorry, well, I should say, this unit is actually energy/momentum. And this lab actually incorporates energy and momentum. And I'm going to explain that to you now. When you see where this whole video starts, not surprisingly, there's a blow dart again coming out of the left side of the video, the same blow dart you saw before. When it comes over here, and where is it? I lost. Oh, there it is. Right there in the middle. One frame later, it's already, boom, it's already hitting it. My point is, what would this type of collision be between the dart and the wood? Would this be an elastic collision that we're seeing, or an inelastic collision between the dart and the wood? Anybody? Yeah. Yeah, because exactly, because it gets stuck. In most cases, that's really what you're looking for. Do they stick together? If so, it's an inelastic collision. And yep, it's a dart and it's wood. So bank, they stick together after the collision. So this is involving, yes, a collision. Yes, it's involving momentum. I'm telling you now, it's involving a inelastic collision. And it's involving energy, because what type of energy is coming into this collision? Is potential energy coming into this collision, or is kinetic energy coming into this collision? In this case, kinetic energy, right? The kinetic energy of the dart is the energy coming into the collision. However, what does that energy turn into when I get to this frame right there? Potential energy, right? Now, again, we see that, like anything, it slows down as it goes up. Those little incremental distances are getting smaller and smaller and smaller because the speed is decreasing as it goes up into the air, which we know should be the case, right? Doesn't matter if there's a road there or you're just throwing a basketball up in the air. If anything's going up, speed should decrease, potential energy increases. So in that way, all of the kinetic energy of this, I'll take that back. Some of the kinetic energy of this dart is turning into potential energy at the end. I couldn't say all because you may or may not remember, but you need to for the tests, that when you have inelastic collision, some energy is lost to heat and to sound and to friction, and that's just something you need to know. There is always some loss of kinetic energy. So if this guy comes in with, right now, here, oops, went the wrong way. If this dart comes in with 10 joules of kinetic energy, if there was no loss of energy due to the collision, then there would be 10 joules of potential energy in this frame here. You'd say conservation of energy. No loss of energy, but they're like, no, but that's actually not right. When we have inelastic collisions, there's always some loss. They're like, all right, so this guy comes in with 10 joules of energy. So you mean up here, there's only like 9 joules of potential energy? Like, yep, that's totally right. Like there's a loss of energy. It might only be 1 joule. It might be 0.1 joules of some small amount. So I'm reminding you that there, just as you go into this lab, that there is some energy loss because it is an inelastic collision. And my bottom line point is that this is a great lab because it has you really use all of the things from the beginning of the energy unit, with collisions, with kinetic energy, with potential energy, with an inelastic collision. They're sticking together, and there's a lot of things to think about, and it's a nice lab for that reason because it incorporates pretty much everything. I didn't want to, I'm not going to tell you exactly how to do it, but I'm just pointing those ideas out to you to be aware of. So you can begin it. You got 20 minutes. Just notice that the question says, make question 1 at least. And I don't think this was a long one. I mean, it might take a little while, but it's not like there's a million parts. There's just this one thing, number 1. We'll read it in a second. And then part 2, oh, you have to submit before you can see part 2. But all right, I'll read part 1. Make measurements from the video and use them to predict the speed which the dart must have been moving before, and when they say before, they mean right before it hit the stick, in order to cause the stick to swing like this. Again, it's vague. They want it to be vague, but I don't want it, When they say, what speed did this dart have to have so the pendulum can swing like this? What they meant is, so the pendulum can arrive up at this height. With what speed does the pendulum have to have in this one last frame right here? And actually, that's as close as they let us get because it's moving so fast. By the time I go to the next frame, it's already stuck in the wood. But they're technically just asking you to predict it with measurements, right? Make measurements from this video and use them to predict the speed that the dart must have had coming into this collision to cause them both to end up at this height up here. That's it. I'm not saying it's easy. I'm just saying that that's all that's asked. That's the only prompt. It's one sentence. Just be aware that they give you the mass right there. Stick has a mass of such and such. Dart has a mass of such and such. I got it there. I'm going to toss you guys into some breakout rooms, and you can talk to each other about it. It's challenging, and again, I don't think it's long. I don't think part 2 has a lot under it once you get to that. But conceptually, like thinking through how you'll solve that, it's challenging. But you can do it. I'll put you in groups for that reason. All right, here we go. Breakout rooms. We'll do 3. All right. I'll be over. And can you guys? You guys are actually in? Can't tell. Let me see. What's that? All right. So I'm going to drop you guys at home into breakout rooms, and then I guess I'll mix you guys in once the people in here join. Yeah. Oh, you're in there now. Sorry, I'm trying to read that. Let me edit rooms. Looks like I lost the class. I don't know. I closed it out, I think. Like I did. Oh, sorry. What's happening? Yeah. You guys, I'm sorry. I don't know. Something weird happened. Oh, you guys are still open over here. All right, guys. I think. Yeah. Sorry that I don't know if you can all hear me or not. Sorry that I went a minute over. Anyways, continue working on this. When I see you guys on Thursday, I'd like to kind of go over this with you. And I'm also going to just point out that we're going to be starting talking about two-dimensional collisions, where something can move, up and down and left and right after a collision. It's called two-dimensional collisions. We're going to start talking about that on Thursday when I see you next. So I'll post something that makes it clear what I'm looking for you guys to do. But just telling you now, I'm hoping that you can have that finished, this lab, by Wednesday night, midnight. Otherwise, have a great day, everybody. I'll see you later. Unless you have questions. Do you have any questions? Anybody? All right. Have a great day, everyone.